So now that you've done a few labs, you've worked with a few different types of remotely sensed data, I'm going to give a rundown of a few multispectral sensors, missions, I guess, that unify those. And it's going to be a little bit of history, but it's going to be the history of the sensor systems that we're still going to use, I guess. So we're not looking at something that might give us a glimpse of 1960s, but rather contemporary change um, with reference to the past, but uh, like I said, still of some interest. We begin with talking about Landsat. Julie Echo calls it the most important Earth observation mission ever, which is probably true. Um, there are a lot of different sensors that have been used on Landsat platforms as part of this mission. And that as we go from the early Landsat 1, 2, 3 up through current Landsat 8, the steps kind of between those are of varying size and in varying dimensions. By dimensions, here I'm talking about kind of the different types of resolution or specs that we covered in previous slides, previous sections of this chapter. So earliest Landsat 1 through 3 relied on sensors up here in the table 3.1. Got a lot of info, um, maybe could be more helpfully organized. So it's got spatial resolution. Down here, you can kind of trace down the columns. And that can vary depending on the band. So here, the MSS, multispectral scanner sensor, is basically a visible, near infrared, a little bit of thermal. Thermal going to be coarser spatial resolution because there's simply less energy in that range. So in order to be able to detect differences precisely, just more energy needs to be observed. So you're going to be looking over a larger area to capture that. 80 meter spatial resolution, or 79 to be precise, for the visible near infrared bands. Now, there's a big step up that's generally a technological achievement between Landsat 3 and 4. And people don't really talk about Landsat 4 as much, simply because it was operable for a shorter period of time than Landsat 5. Landsat 5 being collecting data for 27 years, 1985 to 2012. So a long time. That jump was in a few areas. So one of the areas was additional bands. So of these 7 bands, 6 of them, 1, 2, 3, 4, 5, and 7, are multispectral. So visible up here, 1 through 3, near infrared, 4, or shortwave, 5 and 7. Band 6 is a thermal, and it's at 120 meters compared to 30 for those multispectral sensors bands. 120, a lot coarser than 30, but 4 times smaller than 240 meter spatial resolution. So kind of technological achievement allowing for sensing energy in more bands, so at more locations in the electromagnetic spectrum, more wavelengths to be accurate here, and also higher spatial resolution. The other change is spectral. It relates to spectral, a dimension of the energy, but it's not the number of bands, but it's the width. And so you see here band 1, called the blue band, is looking between 0.45 micrometers and 0.52. So that's a range of 0.07, which is narrower than the 0.1 micrometer that the band 4 in the MSS was looking at. So the narrower these wave bands, the more precisely you can constrain the energy there. What is the green, the blue? The larger they are, the more potential for kind of stark differences to be averaged out, so to speak. Between the thematic mapper, TM, the sensor of onboard Landsat 4 and 5, there were some changes to this enhanced thematic mapper plus, best known for being on board the Landsat 7 platform, but it was also on Landsat 6, which never actually captured usable data. So you can look, and many of the bands are the same. So 1 through 7, same range, corresponding, so it kind of neatly matches up in that way. There is an 8th band, which is actually a finer spatial resolution, 15 meter versus 30, so 1/4 the size of these pixels. And it's got a wider spectral band range, so it's from 0.52 to 0.9, effectively the range of bands 2 plus band 3 plus band 4, so starting at 0.52 micrometers all the way to 0.9. So because it's looking at all reflected energy across a wider band, there's more energy to observe, and thus precise differences in measurement can be made over smaller areas. So that's how finer spatial resolution is allowed. So you still run the risk of kind of ironing out differences, but the benefit is there's more energy across a wider wave band, and so you can get finer spatial resolution. On the other hand, we saw small differences between thematic mapper, ETM+, but there's rather large changes between ETM+ and OLI on board Landsat 8. And so these have to do with more bands. The bands don't match up neatly because there's kind of a coastal blue, coastal band here, observing reflectance over a rather narrow wave band, 0.02 micrometers. Band 2 in OLI corresponds to band 1 in TM and ETM+, a little bit narrower, so just a smaller max at 0.51. Band 3 in OLI corresponds to band 2 in ETM+ and TM, and so on. A little bit different. Even the panchromatic is shifted a bit. I believe it still has the same width, so 0.38. Oh no, not 0.38. It doesn't have the same width, I'm sorry, but still is imaging approximately some red near infrared range, that being band 8 here, and has the same 15-meter spatial resolution. The Landsat 8 has here 2 acronyms, OLI covering the multispectral bands and TIR covering the thermal. And you can see band 10 and 11, there are 2 thermal bands here. It has to do with the way that the data are captured. So there's a section on along track versus across track scanning. So all prior Landsat sensors, prior to Landsat 8, were across track. OLI was a long track. So this is being the multispectral bands. And that I'll show in another slide, just reduces the number of things, mechanical things that can go wrong. Another change between prior sensors and the OLI that you can't really see here is the radiometric resolution. So this being the sensor's ability to precisely differentiate radiance. So that's a lot higher in OLI too. So what's called the signal to noise ratio is higher. And it would allow a panchromatic band, here band 8 at 15 meters, to be better constrained, so narrower waveband here. Now, something that's not in this chart but is discussed in the text of the book is the changes in the way that Landsat data were distributed. So this came about around year 2010, so between Landsat 7 and Landsat 8. Basically, the methods for online distribution versus mailing you a CD or some other data, and even compared to earlier online data distribution, improved greatly. And the cost of data came down. So originally, kind of with the earlier Landsat sensors, data was very expensive. And the only entities that could really afford it on a reliable basis were oil and mineral companies. The cost went down, but still remained high enough that academics, people on like a short string budget, even municipal governments maybe, could only afford the rare image, here and there, maybe before and after, from a time window, but not a large range. And in fact, not all data that had been obtained or had been captured were available to users at all times. So I wrote here basically the Landsat time series ENVI tutorial that we did could not have been done. So there really were very few studies using, say, a 5-year interval period to capture landscape change. It was just hard to get your hands on reliable, processed, comparable input data from similarly spaced periods like that. So this kind of liberalizing use of the data, just making it easier for more people to get it in their hands, to compare images from different times, allowed for different uses. And so, like I said, earliest use of Landsat data was oil and gas companies, mineral companies. Later, you see a lot of work having to do with environmental quality, condition, science applications. And it all has to do with kind of Earth's terrestrial resources. But, in as much as ExxonMobil, Auburn University, and, the World Wildlife Foundation are different entities. Landsat has had kind of a long life, hopefully looks to continue. We get Landsat 9 up before the prior sensors stop capturing data. So by virtue of the 30-meter spatial resolution, some smaller objects are hard to resolve or reliably identify using Landsat data, but it has a fairly large spatial footprint. Here, I'll put this comment in. Images are about 180 kilometers by 180 kilometers. Yo. Sorry about that. Got ahead of myself. So a fairly large area seen in an image. This is from our lab looking at the growth of Las Vegas. So it's kind of tailor-made to understand not only kind of Earth's terrestrial resources, but also land as a resource and our use of them. I mentioned the change between a long track, a cross track scanner to an along track scanner between ETM Plus and OLI. One of the reasons that this is kind of so such an in-demand change is because of a particular mechanical failure on board Landsat 7. And this is a failure of the scan line corrector. So something that would, as the sensor scans back and forth across the direction of movement, would correct for the timing of the movement along track. So it affects the images captured by Landsat 7 in a way that no data are collected for certain pixels. And the pattern is like this, kind of stripes of no data going from the edge, kind of in the, I don't know, north or west northwest side, east southeast side of an image coming in, but not affecting the narrow strip in the middle. Kind of this orientation of the images is an effect of the orbit. So the way that the sensor is moving around the Earth. So these scanline errors, the black bars of no data, they're not affecting the same pixels every time the sensor is traveling over this area. So it's not to say that these data are not useful, but it affects other kinds of properties that we've talked about, like a revisit time. So if you're talking about this whole image in a kind of holistic sense, sure, it's got a 16-day revisit period, 16 days before the sensor is going to pass this location again and take another image. But for some of these pixels, you might have some revisit periods are every 16 days, others every 32 or 48, if there's slight overlaps between the affected locations in subsequent overpasses. And so Landsat 7 data, not from the start, because failure happened after a few years, but since, I believe, 2003, is not an ideal product. So if you had Landsat 5 data for the same place and time, you might prefer to use that. Now, if you have Landsat 8 data, prefer to use that, but you might not. Kind of the timing of data you might need is maybe better served by Landsat 7. It can also lead to some artifacts. So if you ever see kind of lines, say, in a classified product that are at this orientation, so kind of slightly higher to the left, getting slightly lower to the right, know that that product, you at least use some Landsat 7 input data. Kind of mechanism that failed would correct the positioning of a mirror here inside the sensor as it would move so that the area on the surface of the Earth where energy was reflected up to the sensor was coming from would be changed. So they call this kind of a sensor, characteristic of all Landsat sensors up until OLI, the across-track sensor. So it required a relatively simple array that was measuring the energy, and the mirror constrained the precise location from which the energy was coming from, and would move back and forth as the satellite would move, so very quickly. So that kind of each pixel or each location, the instantaneous field of view would change. So the kind of more desirable, but also maybe more complicated way of capturing information is through a kind of a multi-part array up at the sensor, where reflected energy is being recorded for all areas instantaneously, kind of across the track of the sensor's movement. And so what you get are, for each array, you get a series of along track records. So that along track, across track being with respect to the direction of satellite movement. Next, I'll talk about the European Space Agency missions, one called SPOT, and then Sentinel-2. So these are what we'd call, or what we characterize as, moderate spatial resolution multispectral sensors. And as such, they're best understood as through a comparison to Landsat. So for SPOT, fewer bands than Landsat, it's kind of a visible near-infrared sensor. This isn't the case for Sentinel-2. Um, both sensors have higher spatial resolution than Landsat does. So this leads to smaller images, about 60 kilometers by 60 kilometers, compared to 180 by 180. Um, Spot has the capability of off-nadir viewing. So kind of just as a mirror is used here to make record of any kind of reflectance along the track of the sensor, mirrors can be used to image areas not only just below the sensor, but also at an angle. So through doing, you can constrain the elevation of the surface. And also um, effectively shorten the revisit period. So even though the sensor won't actually pass over the same location for another, I believe, 18 days for spot, by capturing an angle observation, you can get an image for that same location much sooner. It just won't be directly below the sensor. So it wouldn't need to be corrected in some way for the geometry. Sentinel-2 effectively can give a shorter revisit period by virtue of having multiple sensors in that constellation. So the 10 or 20 meter spatial resolution of these sensors makes them, compared to Landsat, better for resolving certain features. But these being roads, much easier to spot in the Sentinel-2 data than in Landsat. Small fields to tell the difference or to tell that they're fields, and many types of buildings. With Landsat, it can be hard to identify, the area of a specific or a discrete building. Less difficult for Spot and Sentinel. Technically, the data archive is not as long as Landsat's. Landsat's going back into the 70s, but in terms of the use of Landsat data, most of the data that you'd see used comes from a thematic mapper at the earliest. So the spot data dating from 1986 is comparable to the earliest thematic mapper data. Although the as you can see in the book shows this, I didn't pull up the table here, but there has also been technological development in the spot sensors. Something I'll note, Sentinel-2, in contrast to the way that Landsat sensors get numbered or platforms get numbered, it's not really like the descendant of Sentinel-1. So Sentinel-1 is a radar sensor, active C-band synthetic aperture radar. And so it launched before Sentinel-1, but it's meant as kind of a complementary mission and rather than kind of a precursor. Something I'll go back to mention about Landsat, just the development, is that in some ways the step from ETM plus to OLI was great, but in other ways it's fairly similar. So you're still looking at a 30-meter product. And I'll just mention here that if you go just by what is available technologically, OLI is not pushing the limits in all areas of that. So it would have been possible to kind of reduce the spatial resolution at which bands 1 through 7 and 9 were capturing information. But doing so would complicate the process of relating that data or comparing that data to earlier products from TM or ETM plus. So the maintenance of a 30-meter spatial resolution isn't really like a limit of the technology, but rather it's a purposeful design to ensure data continuity, something that kind of complements data distribution practices to, again, enable things like our ENFI tutorial. Finally, I'll talk about high resolution, really kind of high spatial resolution, commercial satellites. And there's kind of two areas I'll mention now, and you've seen data from one of these. And The other actually is more recent than the textbook. And so what we'll do is we'll look into that later on. So the first era, here I say from about 5 to 25 years ago, the kind of market space, and I should be careful with this terminology, of producing high spatial resolution data between about 1 and 4 meters pixel size was dominated by a few private companies, and they build a sensor, not just one necessarily, but pretty unique sensors. So there wasn't an idea of continuity. Rather, the sensors were meant to improve vastly on what had been available. Um, it's a selling point. Increase the spatial resolution, radiometric resolution, the number of bands. And these, by virtue of their spatial resolution, their orbit, the kind of nadir overpass time, revisit period would be very long. But these sensors could be angled. So they would be tasked based on whoever's paying the companies to capture images of locations that the satellites were not passing directly over. So that's what we mean by off nadir. Nadir being immediately below the sensor. So they could be angled to capture off nadir images. So companies would get money for this task, but after a period of time, for many of them, the companies would set up things like one is called the Digital Globe Foundation to share and distribute the data. So if you need some data for a project, you probably, unless you have a good budget, can't get it from these sensors. But if it's from some period in the past, they have map applications. You can go in, see what's available, and make a request for free older data. So during this span, I guess, 5 to 25 years, there were a lot of consolidation of companies. So kind of Digital Globe bought out others. And maybe, I don't know exactly when it would start, but I'd say about 5 years ago, maybe 6, maybe 7, there's a new initiative called Planet Labs. And this is kind of enabled by venture capital funding. So I don't think they make money per se, but they definitely make data. And so this model is based around something called a microsat. So again, this isn't leading edge technology, but it's something that hasn't been available in the future or in the past. Sorry, kind of smaller. People call them shoebox satellites. Are sent up, and when you have a lot of these, they form a constellation that can capture data for a given location very often. And I think they really ramped this up in 2018. There's a very, very steep curve of how many of these microsats they had up through time. It's a little bit complicated because the number isn't even through time. But if you look in the last few years, Planet can provide multispectral data, so visible near infrared, at about 4 meters of spatial resolution, but they can provide these images daily. So it's an interesting kind of space. I don't know what the largest clients are. I've seen a lot of it academic, humanitarian use. It's interesting because of just the volume of data. You never could have worked with this decades ago, just given kind of computational power. But still, some of the issues with working with the data are some of the ones that that would arise decades ago with Landsat data. So kind of difficulties of relating kind of observations of the Earth's surface made at different moments in time with the different position of the sensor, of the sun, of the atmosphere, of all those things. So these kind of high spatial resolution data found applications in agriculture, so understanding kind of where in a given field the crops are doing better or worse, and kind of figuring out what kind of interventions are appropriate for the poorer performing areas, useful in disaster relief, infrastructure, so any kind of governance, spying, so kind of military and I don't know, intelligence operations, and then kind of question marks. So we'll see. Kind of this thing with Planet Labs. I don't know exactly what their schedule for making money is, but let's see if there's a need, figure it out. And then we've seen these data used in a kind of getting to know NV tutorial. So here, kind of where you could distinguish kind of, I don't know, new developments with Landsat data pretty easily. And in Sentinel data, you could maybe identify roads better, buildings. With the high res data, you're looking at seats in an amphitheater or kind of paths on I don't know what this would be, a golf course, something, and or softball fields. That's what it would be. Or and when you're looking at kind of tree crowns, you can see how sometimes this data at this spatial resolution might be too fine. So you're not only seeing the kind of bright green, photosynthetically active, productive leaves, but you're seeing a lot of shadow in there. So these are kind of the different data products, a little bit more about how they're generated. And by now, as I said, we've seen them in practice, we've worked with them. So we have a good idea about what different products can and can't reliably help us do, but maybe also some of the strengths as well.